Hi everyone, Mary here, and this time we're going to talk about wave boundaries. When a wave travels from one material or medium into a new or different material or medium, three different things happen: reflection, transmission, and absorption of the wave energy. Now, how much of each one of these, reflection, transmission, and absorption, occurs depends upon the kind of wave. Do you have a sound wave? Do you have a light wave, compressional, transverse? The nature of the wave boundary. Are you going from air into water? Are you going from water into steel? Are you going from steel into jello? Whatever the heck the wave boundary is, that's going to have an effect. And then the angle of the interface. Are you hitting something straight on, or is it reflected at some sort of a wild angle? I love this illustration right here because this shows three different laser beams, a red, green, and blue laser. And this looks very much like an air to water boundary. And one of the things you can see is as a laser beam comes in, you get some of the reflected energy is reflected, and some of the wave energy is transmitted into the new material. Now, the green laser, some of the reflected energy comes out and some is transmitted. The blue light, I personally cannot see in this particular image any reflected light. Now, it might be there and it might be an effect of the image, but the light itself, what frequency or wavelength, that's going to have an effect as well. This would be a great question to ask on a quiz. What three things happen at every wave boundary? And it's something that once you have it, it can be used to explain so many different phenomena. Here are a couple examples. When you talk about light hitting the surface of water, some of that light, of those light waves, are going to come back and are going to be reflected back into your eye when you're looking down into a pool of water. But some of the light does go down into the water, which allows you to see the rocks and the silt and the fish that happen to be down underneath the water. Another good example of these multiple things happening at a wave boundary is when you look through a window. Now, this gentleman happens to be looking out a window during daylight. Now, during daylight, as he looks out, some of the light from inside his room is going out and reflected and coming back into the room. And some of the light from his room is going out into the outside. But he doesn't see this reflected light because during the day when the sun is out, the amount of light that is coming through his window is so overpowering compared to reflected light that all this gentleman is seeing is the light coming through the window. Now, this fellow down here, he sees his reflection in this window because of the fact that it's dark outside. And in the evening when it's dark outside, the quantity of reflected light, which is the same amount of reflected light you get in the above situation, is bigger than the small amount of light that's coming through maybe a very dim window into a closed store or something like that. So there's a whole bunch of situations where you get reflection and transmission that's occurring. And by looking at what's exactly going on, you help analyze the entire wave situation. Let's talk about sound. Now, sound itself likes to reflect off of hard, dense materials. Classic example is if you go for a walk in an unoccupied building or apartment or home. There are no soft furnishings, there are no curtains, and it has a very hollow, echoey sound. An echo is nothing but a reflected sound. You take a room and you put carpets and draperies and soft furnishings in the room, the whole sound quality changes because the soft, squishy stuff is going to absorb sound much better when the hard, dense materials are going to reflect that sound. Acoustics is the study of sound and its effects. How do you maximize reflections and how do you maximize absorptions for whatever you want? Now, if you were in band or choir as a child or growing up in high school, you may have had these white sound reflective partitions that were behind your band or behind your choir. The purpose is to reflect the sound waves that are going away from the audience and send that sound back out to the audience to give a nice, rich, fuller, louder sound. A lot of communities are going to have band shells, and they're called shells because they're kind of half a shell, half a clamshell sort of shape. The purpose is to amplify the sound. The musicians are playing or singing to the audience, but sounds that would be lost going backwards get reflected by this hard surface and are sent back out to the audience and amplify the sound. Now, if you have a big concert hall, this is a fancy, of course, concert hall here on the left, there are a lot of hard surfaces designed to reflect sound, but notice all of the squishy, soft seats. What are the purpose of the soft seats? And you would imagine that the soft seats are there for the comfort of the patrons or the audience. Yes, to some extent, but a great extent, the reason the soft seating is in an auditorium is so that the orchestra, when it practices, has very similar acoustics from performance to practice. If they practice with soft, squishy seats, they are going to use the softness of the seats to mimic the squishiness and the softness of all of the humans that are going to be occupying the audience during a performance. It gives a much truer sound to the musicians of what it will actually sound like with a full or packed house. Reverberations. Definition of reverberation is a small, quick, reflected sound. And many of them sound really, really good to the human ear. We like the sound of reverberations. Many of them sound rich and they add fullness to sound. This is why people sound better in the shower. If you are sitting in an audience and you hear someone's musical talent and you hear that sound directly, they might sound fabulous, but you put them in a concert hall where there are nice hard surfaces on the ceilings and the walls and the back behind the musician. All of these quick reflections make that sound richer and fuller. And that's why a concert hall can be designed to have really great sound. A lot of electronic musical enhancing devices that you might have to help with music will have a reverb box or a reverb button, and it takes the musical signal, delays it a fraction of an instant, and gives it back to you, and it simulates that big concert hall sound. Same thing, those white reflectors behind this elementary school choir adds that richness to the thin and small voices of small children. Ultrasound. A gel is typically used between the transducer and the patient when an ultrasound exam is taking place. What's the purpose of the gel? The purpose of the gel is to produce minimum loss of wave energy going from one medium to another. Because if it went from transducer into patient and there was an air gap in between, lots of wave energy would be lost. By putting a gel in there that has a similar acoustic signature as human, it is going to minimize the loss of wave energy and produce a much better ultrasound signal. The law of reflection. The law of reflection is something that you're going to see in a variety of different wave phenomenon. It looks very much like a ball bouncing off the floor. And the law of reflection says that when a wave hits a smooth surface, the angle of incidence is going to be equal to the angle of reflection. Now, the angle of incidence and reflection, instead of being measured from the surface, is actually measured from the normal. If you remember from earlier in physics, the normal is a perpendicular drawn to the surface. And the reason we measure these angles from the normal and not from the surface is because the law of reflection is obeyed by waves when they bounce, whether you are talking about a flat surface or you're talking about a curved mirror or you're talking about any sort of a weird and crazy surface. Let's talk about what happens to waves when they hit different materials. If you have a transverse wave and it hits something that is more dense, the wave inverts. That means it turns over. Here's what I mean. Let's say I have a wave that's coming in and traveling towards a more dense material. So as the wave approaches, it's going to be on the top for our illustrations. When it hits something more dense, the wave is going to invert 180 degrees. It's actually going to turn upside down. Why is this important? Well, everything from lasers to colorful soap bubbles, we have to know this in order to explain what we see with transverse waves. If you have a wave reflected off of a material that is less dense, so let's say I have a wave coming in and it's going in like this, and it's hitting something that is a less dense material, less rigid, it is going to reflect upright. Same thing, it is going like everything from lasers to soap bubbles and optics and light. You need to have an understanding of this phenomenon in order to truly explain what's going on. Those of you who are taking the hybrid version or face-to-face version of the class, we're going to see this with slinkies. And if you have a slinky pulse and you have one material, let's say a slinky, and you are attaching this to something else like a thin string, and you send a wave pulse in, and this is a knot. So this is an interface between two different materials. Weird and crazy things occur. When the wave comes and hits this interface, you get reflection, transmission, and absorption. So when the wave hits, part of the wave energy, a little bit of it, a little tiny bit of it, gets reflected. Some of the wave energy gets transmitted into the new material. Now, this is fun to see with slinkies because you can physically see it. If it gets sent into a different kind of material, let's say this is a material where there is less transmission. This is our incoming pulse. Here's our knot. Here's our interface between two materials. The wave pulse comes in, you get a big reflection and a very small transmission. What determines what situation you have, a big transmission or a little one? It depends on the matching, how close one material is in property to the next material. If they are very, very close, you're going to have almost perfect transmission. If they're very, very different, you're going to have very small transmission. All right, that will do for this section, and we will see you later. Bye-bye.